Hi, welcome to lecture 9 titled Overview of Zynq MPSoC Architecture. And throughout the following video and beyond also, we will explore the inner workings of Zynq MPSoC and focusing on the vast variety of features and resources it provides to the world of embedded applications and embedded AI solutions. We will particularly pay attention to the EV device. It's a device family which we'll explore in some later slides, and the similarities this has with the other devices in the Zynq MPSoC range. And by the end of this video, you will have a great understanding of all the elements that combine to form the Zynq MPSoC architecture. You will further be aware of the various processing features available, and so that you may be able to design your own embedded applications within the MPSoC world. So firstly, we'll begin introducing the range of different MPSoC devices available, and we will then examine the Zynq MPSoC architecture by introducing the APU and the RPU, which is application processing unit and real-time processing unit. And we'll also look at the programmable logic, the configuration security unit, and also the platform management unit. So discussing about the Zynq MPSoC device families, all Zynq MPSoC device families contain what is called as the PS. So you can see that the Zynq families contain the processing system in both the cases, and the PS is dedicated and optimized silicon element within the device containing many different processing units and platform management and security systems. The PL, on the other hand, which you see in yellow, exists as a programmable region of FPGA fabric and capable of accelerating arbitrary logic functions and is reconfigurable during runtime. So at the time of recording this video, there are three different Zynq MPSoC device families available, and each shares similar fundamental concepts that they have the PS and the PL. The device families are known as the CG devices, EG devices, and the EV devices. And they are fundamentally same but share some variations, like they do not share the variations but are different in their structure of how they are made. We will begin by first discussing the difference between the PS of each family and then explore the changes present in the PL. So in the CG device family, you can see that, sorry, in the CG device, you can see that we have a dual core RPU and a dual core APU Cortex A53 processor available, and the RPU processor is R5. For the EG devices, we have the same dual core RPU, but along with that, we have an APU quad core Cortex A53 and a GPU Mali 400, which is again by ARM. For the EV devices, we have RPU of the same configuration, APU quad core Cortex A53, same as the EG device, the GPU, but along with that, in the PL, we have the silicon optimized for video coding and decoding for the H264 and H265 formats. So let's look at the slide here. So in only EV devices, we have H264, 265 available. And as far as we talk about the PL logic cells available, they are of the range 100K to 600K in the CG devices. So there are multiple. So these are the device families. Inside them, depending on your use case or your application scenario, you can choose different variations within the family, the different models. So as we begin to understand the overview of the Zynq architecture, one thing which we have to be clear is with the documentation. So there, like as you're designing your own embedded system with the Zynq MPSoC, you will see that we are using the ARM processor inside it, and both ARM and AMD, like Xilinx, which is the which is the company which has been acquired by AMD. So both ARM and Xilinx, they provide reference manuals for their products, and which will support you in different ways. But there are certain differences which we need to understand between the two. So let me just first of all show you the documentation. So here you see the documentation which is of the processor Cortex A53, which is given by ARM. It is available in this website, and you can go to and see all the features which are available in this, including how the instruction fetch unit works, data processing unit, and SIMD and floating point extensions, cryptographic instructions. You can look at the programmer's model, and you can basically explore the memory model and everything. So this is the uh, documentation which is provided by ARM. On the other hand, the documentation which is provided by Xilinx looks somewhat different. So in order to understand the difference between the two documentations, you have to understand that how the ARM licensing works. So ARM license is used for the ARM license which they give is to for their processor intellectual property IP to original equipment manufacturers OEMs such as Xilinx and Cypress Semiconductors, ABB. There are many companies which use the ARM processor. So all of them are called as OEMs. So the Zynq MPSoC contains both a Cortex A53 belonging to ARM and Cortex R5 again belonging to ARM processor, which are specifically based on this ARM instruction architectures, which is ARM V8 and ARM V7 respectively. So upon selecting the processor which the OEM wants to include in their product, the ARM gives them the flexibility to customize it based on their end goal or end application. So the difference which you see here between the two documentations is exactly how the customization has taken place and the ports which they have named according to their implementation. So the Zynq MPSoC also contains additional ARM IP that may have also undergone particular customizations, and all those the tables which you see here, if you are working with particular board, then it is better to view the documentation of that board rather than looking at the generic implementation or documentation of the ARM processor. So with this thing in mind, we will discuss what you should expect from ARM and Xilinx documentation. And so both the documentations include the fundamentals of underlying ARM architecture principles and processor core customizations with existing processing elements and optional extensions. Consultation with several ARM documents and manuals will provide a better understanding of the ARM processor IP. However, will not give the exact implementation or the information which the OEM like Xilinx has used for their configuration. Xilinx documentation will provide information on the specific MPSoC details and implementation, such as the changes made by them, particularly related to the signals and ports. So this technical reference manual which you see UG1 is 1085. This is particularly useful for us in understanding. If you explore this documentation, you will see that you will have all the particular signals, interfaces and pins and the ARM8 architecture explanation, which is very similar to the documentation which you saw here or the diagram which you saw here in features, interfaces, like here we had seen. So this is also technical reference manual itself, and yes, this is the image which is very similar to the image you see here. So we now have a better understanding of the Zynq MPSoC device families, and the hardware variations are also especially notable within the different families, especially within the PS, which is like the different speeds and the quantity of application processing cores available. So to examine the structure of the Zynq MPSoC device, we will study the family containing the most number of features at this time, which is the EV family. So this architecture which you see is of the EV device family and will serve as an example through the rest of the video and the sections. We will mention differences in the architecture between the device families wherever it is necessary, and additionally throughout the lifespan of the Zynq MPSoC, it is possible that the new devices will be released and rolled out, and it is still being manufactured today with because it is really efficient architecture, although they have moved to 7 nanometer technology, but this Zynq MPSoC architecture, which is based on 16 nanometer technology, is still quite widely used. So this figure which you see is a simplified overview of the Zynq MPSoC architecture. And from the previous section and from the previous video, we have seen about the APU, RPU, and the GPU, which you can see here, which is quite easily identifiable in this diagram. So each processing unit is connected to an interconnect which is known as the cache coherency interconnect (CCI), and the CCI is helpful addition to the PS architecture and allows the processors to share tasks and data between one another dynamically. Primarily, the CCI is used to achieve asymmetric processing, fundamentally providing interconnect support for coherency between processing tasks and ensuring each core operates on the most up-to-date data across the entire PS. So you can see again in this slide, it is summarized the utility of cache coherency interconnect, which allows processors to share tasks and data between one another dynamically and is used for to achieve asymmetric processing, which fundamentally provides interconnect support for coherency between the processing tasks and ensuring each core operates on the most up-to-date data across the entire PS. So further, the Zynq MPSoC device in the EG and EV families, they contain the ARM Mali 400 MP2 GPU, and the GPU is capable of accelerating both 2D and 3D graphics and includes a geometry processor and two pixel processors. So this GPU supports the OpenGL and OpenVG APIs, allowing the APU to offload graphic processing tasks to the GPU. So let's quickly discuss about the OpenGL and OpenVG library, because it's one of the use cases of the GPU processor which is available. So OpenGL library stands for Open Graphics Library, and the purpose of this is to provide a cross-platform API for rendering 2D and 3D vector graphics. And it's widely used in gaming, simulations, and CAD applications. The features of it are focused on hardware accelerated rendering of complex 3D graphics, shading, lighting, and textures. On the other hand, OpenVG stands for Open Vector Graphics, and it's a cross-platform API specifically designed for hardware-accelerated 2D vector graphics and aimed at smooth rendering of curves, shapes, and text. And the emphasis of rendering 2D vector graphics is for like fonts, scalable icons, and UI elements with anti-aliasing and high-quality texture rendering. Also, the use cases of this include 3D modeling, video games, virtual reality, and scientific visualization. As for the OpenVG, it's used for user interfaces, digital dashboards, vector-based graphics, and embedded systems like smartphones and e-readers. The performance for OpenGL is optimized for high performance rendering on GPUs with large developer community and extensive support. For here, the performance is highly efficient for 2D vector graphics with low power consumption, making it suitable for embedded systems and the basic GUI. So typical code of how OpenGL library looks like is this. You have C codes, and when you compile this C code, it will actually execute on the GPU. Going back to the basic overview architecture, let's understand few of the other important elements. So the general and high-speed connectivity for the PS is also available, and which allows for the PS to interface and communicate with off-chip components. You can see the general purpose peripherals written here. So this connectivity is achieved through what is called as multiplexed input-output MIO pins. High-speed connectivity uses a multi-gigabit transmit, and this you can see on this part, the high-speed peripheral. This together is known as PS GTR transceiver. So general and high-speed peripheral interface blocks which use the above connectivity are also discussed later in the video. There are many more resources within the PS than shown in this particular figure. The APU and RPU in themselves consist of additional interconnects, memories, interfaces, controllers, and other associated processing elements required. There is also a dedicated platform management unit, which you can see on the bottom here, and a configuration security unit. And there is also a battery power unit, which helps for the efficient battery optimization. So in addition to the physical processing resources within the PS, power domains and communication paths between the processing elements are also of great importance, which are not highlighted in this particular diagram. So now let's dive into one of the most important parts of the PS, which is the application processing unit. So now we'll discuss the architecture of application processing unit, which is in short called the APU. So the APU houses the ARM Cortex A53 multiprocessor core, and within the EG and EV devices there are 4 cores, and while the CG devices contain just core 0 and core 1. This figure illustrates a simplified diagram of the entire APU. So each Cortex core comprises of the following computational units. It has a floating point unit, a neon media processing engine, which is called MPE. It has a cryptography extension for doing all the encryption, decryption, crypto related tasks. It has a memory management unit. It has a dedicated L1 cache. One cache is for the I cache, which you see is for the caching the instructions, and the D cache is for caching the data. And the remainder of the APU consists of a Snoop control unit and a level 2 cache memory, which you can see here. So each of these ARM Cortex A53 can operate up to 1.5 gigahertz and supports 32-bit and 64-bit instruction sets. The software can use 64-bit instruction set and achieve access to physical memory space, which is approx 4 GB. All four cores contain their own FPU, Neon, and crypto computation units and separate 32 KB L1 cache, which you can see here. So besides having their own FPU, Neon, and crypto computation units and separate L1 cache for all the cores, they have their own debug and timing resources, and all these cores can be independently accessed for debugging using the JTAG port. The MMU is primarily used to translate between the virtual and the physical address space. So what is the purpose of level 1 cache? The level 1 cache memories allow processing cores to locally store commonly used data and instructions so they may be retrieved quickly. All four cores share the level 2 cache memory of 1 MB for further storage of data and instructions. As all cores share the level 2 cache memory, it allows them to communicate with one another without use of the external memory. The Snoop control unit governs and controls the access between all the cores and the level 2 cache. The SCU helps maintain the coherency of data between the L1 data cache of a processing core and the level 2 cache memory. And it can achieve this without reading and writing to external memory due to internal buffers allowing to direct cache to cache transfer. And in addition to this, the SCU also manages transaction between the APU and the PL via the accelerator coherency port. As we had discussed about the cache coherency interconnect, the CCI within the Zynq MPSoC is connected to the APU's master bus interface using a 128-bit AXI coherency extension, which is known as the ACE port, AXI coherency extension master. This ACE protocol allows the APU's master interface to access the given address space and retrieve up to date data. The data may be copied locally to L1 cache or to the L2 cache memories to optimize processor performance. So if you're accessing a data at a particular memory location from the external memory, then this port can bring in the data of nearby memories to the L1 cache and to the L2 cache for quicker access. Also, the Neon Media Processing Engine is an extension to ARM Series A processor only, which provides advanced single instruction multiple data facilities, popularly called as SIMD facility. So single instruction multiple data technology has been designed to accelerate large vector operations typically found in multimedia, where on a single, on multiple data, you have to perform single instruction. And it is also quite common in the DSP style algorithms. The single instruction multiple data also support the Neon processor to operate on the elements of two input vectors to produce a corresponding output vector. One instruction is used to configure the Neon processor to perform the same operation on multiple data elements of the same type and size. Talking a little bit about the crypto core, it is a dedicated encryption decryption tool which supports again SIMD instruction sets. Standards supported are like AES, which is Advanced Encryption Standard, the Secure Hash Algorithm, which is popularly known as SHA, and in that multiple branches of it like SHA-1, SHA-224, SHA-256, and also the most popular RSA algorithm. Crypto also supports finite field arithmetic used in algorithms such as the counter or the elliptic curve cryptography. We'll dedicatedly study the cryptography part of this processor in some of the later video. And finally, the APU uses an external general interrupt controller known as GIC to support system interrupts. This GIC is the ARM Core Link GIC 400 IP, which is based on the GIC V2 specification. It's just a little finer detail. Primarily, the GIC provides the APU with registers that manage interrupt sources, behavior, and routing between the processors. This is like an overview to the APU architecture. We'll go into more depths of how to program APU in later video. So based on the discussion, there are certain recap points for you to actually read and recall. This is from the lecture itself. All right, so now let's start discussing the real-time processing unit. So this is the architecture overview of the real-time processing unit, and RPU contains a dual-core R5 processor. This is core 0, this is core 1, and this processor is particularly meant for real-time applications. The RPU's architecture provides low latency operations and deterministic performance throughout the entire unit, which is the main highlight for any real-time processing unit. So on, you see here in the blue, the core R5 contains a floating point unit, and this is meant for the single and double precision arithmetic. The level 1 memory of each Cortex R5 core contains 3 tightly coupled memories called as TCMs. It consists of two 32 KB caches for data and instruction, and it also contains a memory protection unit called MPU. The Cortex R5 processing cores within the RPU can operate up to 600 MHz in EV and EG devices and up to 533 MHz in the CG devices. So there is a connection between the R5 processor cores and the low power switch which you see here. This low power switch is further connected to on-chip memory and input and output unit, and this connectivity allows the RPU, the IOU and the OCM to operate together while the Zynq MPSoC device is in low power mode. As we'll discuss further that the FPGA, in order to save its power, can operate either in low power domain or in full power domain. So as RPU is part of low power domain, it is entirely and fully operational when the Zynq MPSoC is in low power mode. So there are two primary configurations in which the Cortex R5 processors may execute the software, maybe the free RTOS which is running on them. So it might be the split mode of operation, which allows each processor to work independently, permitting each core to maximize the processing performance and latency. And there can be a lockstep mode which executes the same instructions on both processors. Carrying out instructions in this manner provides redundancy, as if there is a mismatch between the output of the two cores, then an error has occurred. So this lockstep mode method of processing allows a more safety based processing, and is also known as safety mode because it allows the system to determine errors effectively if the two outputs are not matching. There are also ECC schemes. ECC stands for Error Checking and Correction Scheme, which also provide further error detection and correction support. Within the data set or associated code bits, it is possible to detect up to 2 errors and correct 1 error. It has a very popular name, just for this is for your knowledge. It is known as SEC-DED. SEC stands for single error correction and DED stands for double error detection. We'll discuss certain more cryptographic things and checking in later video, where we discuss the safety features and techniques. Also, the level 1 data and instruction caches store local data for increased processing performance, as we have seen it already in APU. And to achieve deterministic processing, TCMs are used to provide predictable data loading times to ensure instructions execute on schedule. Those who have studied RTOS and have interacted with a real-time processing unit, they know that the TCM, which stands for tightly coupled memory, is a form of RAM, and it is divided into two banks, which is labeled as ARAM and BRAM, and BRAM is further divided into two parts, which is B1 and B0. And both of these A bank and B bank are concurrently accessed by the load store unit. And this concurrent access is possible because each memory bank has dedicated ports connected to the load store unit. And the TCM blocks labeled A have 64 KB addressable space, while the blocks labeled B have 32 KB addressable space. The memory protection unit manages access requests to level 1 memory and external memory, permitting customizations and partitioning of memory into regions, which is for protected mode of operation. The regions may then be assigned individual properties, and it is also possible to disable the MPU entirely, which will remove memory access management and set areas of memory to their default properties. Just like APU, here also we have a generic interrupt controller called GIC, but this GIC is based on GIC V1 specification as compared to the APU, which was on GIC 2 specification. Using this GIC, we can control the outgoing and the incoming interrupts from other processing units of the Zynq MPSoC device, maybe from the APU or from certain IO banks or from the on-chip memory. The alignment of GIC's base address is to the base address of the low latency peripheral port, which is popularly called as LLPP port of each Cortex R5 processing core. You can see the low latency peripheral port marked here. The GIC's base address is particularly mapped to the base address of this port, as it ensures that there is low latency access to incoming and outgoing interrupts. The architecture of RPU we'll discuss in detail in one of the further videos. For the sake of completeness, we'll be discussing the graphic processing in it, although we'll not be using it that much. So the GPU which we have available with us in the Zynq MPSoC device is ARM Mali 400 MP2 GPU, and we've already discussed somewhat that it consists of a geometry processor which is called as GP and two pixel processors called PP. The units uses three integrated memory management units, one per processor, and a level 2 cache to store data intermediately. So the GPU can achieve two-dimensional and three-dimensional graphic acceleration, and it is clocked about 667 megahertz. It supports the famous OpenGL and OpenVG APIs, which allow intensive graphics processing to be offloaded to the GPU. We've already discussed the OpenGL and OpenVG in this video. This we can see in this diagram that the level 2 cache is shared among all the processors and is of 64 KB size, and it has an connection to the advanced peripheral bus slave interface. So the APB allows other devices acting as master to control the level 2 cache. So having discussed the APU, the RPU and the GPU's architecture, now is the time to discuss the connectivity between the PS and the external world. So the Zynq MPSoC PS has many different interfaces for connecting to the peripherals, and similar to the older version of Zynq, it has a general peripheral connectivity which is primarily achieved through the multiplexed input output, which is popularly called as MIO. The MIO provides a flexible interface that configures the mapping between pins and the peripheral interfaces. So the pins you can see are available on the external board, which are 78 in number, and through the multiplex input output, these pins are mapped to the peripheral interfaces. 78 of the processing system IOs are mapped to the external peripherals via the MIO. High-speed serial connectivity is to peripherals requires multi-gigabit communication, and it can be achieved using the serial input-output unit, popularly called as SIOU, and it is found within the Zynq MPSoC PS, and therefore we are discussing it here itself. The SIOU is the high-speed serial interface block which supports PCIe, the SATA port, the Ethernet, the USB, and the display port. Particular connections from the MIO can be made accessible to the PL via the EMIO, which stands for Extended Multiplex Input Output. The EMIO creates a direct path of communication between the peripheral interfaces to the PL resources. So we can see that all of this IOU, SIOU are connected through low power domain switch. So let's discuss the multiplexed input output MIO in more detail. The MIO can be thought of as a very large multiplexer, which you can see here in yellow, and it is capable of routing several different peripheral interfaces, which are contained in the peripheral interface block (PIB) to a set of 78 pins. As we can see here that there are different peripheral interfaces like Ethernet, USB, NAND, SD, eMMC, Quad, SPI, CAN, I2C, UART, and GPIO. These peripheral interfaces can be multiplexed using the 78 pins available here. The MI also shares the bank with the USB 3.0 and Ethernet peripheral interface blocks with the SIOU. Not all of these peripherals can be enabled at once because they're just 78 pins. So depending on which subset you want to use, you can map those 78 pins to enable that peripheral interface. The UART IO interface, it is 2 in number, and it stands for Universal Asynchronous Receiver Transmitter, which is used for low rate data modem interfaces, and it is used for serial communication. It often is used for terminal connections to a host PC. The SPI, that is also 2 in number, and it's a standard for serial communication, and it is based on a 4-pin interface and can be used either in master or slave mode. The CAN peripheral interface is for controller area network, and it's a popular bus interface controller compliant with the ISO standards. I2C again is a popular bus specification which is compliant with the I2C communication protocol, and it also supports the master and the slave modes. We have the GPIO ports available with us, and there are 3 banks of GPIO, each having 26 bits. Besides that, we have the Ethernet port, the Ethernet MAC peripheral port, which supports up to 10 Mbps, 100 Mbps, or 1 Gbps nodes depending on the version. Also, we have the NAND flash memory interface, which supports for NAND flash memory and Open NAND flash interface. We have the USB with us, which is compliant with the USB 3.2 and can be used as a host or a device, or can be used as a can be used flexibly. We have this secure digital and embedded multimedia card memory interface, which supports the SD card 3.2 and eMMC version 4. Lastly, we have a quad SPI, which is quad serial peripheral interface, which is a serial communication based on the SPI standard that uses a quad IO, which is a 4-bit data bus, and this increases data throughput so that it is faster than the standard SPI interface. Here is a table summarizing the list of general connectivity IO peripheral interfaces which are available for multiplex input output. Now let's discuss the serial input output unit. The SIU contains 4 high-speed peripheral controllers that each use a single multi-gigabit transmit and receive channel pair known as the PS-GTR transceiver. So this PS-GTR is capable of supporting data rates up to 6 Gbps, and therefore it is called as high-speed peripheral interface. This PS-GTR can connect to any of these peripheral blocks like PCIe, SATA, Ethernet, USB, or display port using the interconnect matrix. Since there are 4 PS-GTR, so at a time only 4 of them can be connected. Let's look at the list of high-speed connectivity input-output peripherals for the SIO. First, we have a display port. So the display port interface is a digital display interface primarily used to carry video, but it can also be used for audio, USB, and other forms of data. It has up to 2 channels which can be interfaced to the PS-GTR transceivers. Next, we have the universal serial bus, which is compliant with the USB 3.2 as we have already discussed. We have the SATA port as well, which is serial advanced technology attachment. The SATA uses different wire pairs for serial communication, primarily with storage devices at rates of 1.5, 3.1, 6 Gbps, depending on the SATA generation. We have a very popular interconnect, which is known as Peripheral Component Interconnect Express, which is standard for high-speed serial computer expansion communications. And most of the modern GPUs connect to the motherboards using this interface. And then we have the Ethernet interface as already discussed. We'll wind up the discussion of the overview of architecture of Zynq MPSoC with all the components we have discussed from the PS perspective. Inside the PS, there are 2 more components which are remaining for us to be discussed. I'll just open that diagram. So in this, we can see that there is a platform management unit and a configuration security unit which is yet to be discussed. In further video, we'll discuss about the programmable logic and the fabric which is inside the programmable logic, and also the DDR controllers. We'll have a short discussion on the PMU and CSU as well, and we'll get an overview of the entire Zynq MPSoC architecture. So thank you for watching this video.